I should start by saying that I decided to take advantage of the concept of the conference, that it's like Özlem said, there are different kind of mathematicians here. So I'm partially talking about some older work, which somehow I never really talked about in the conferences because it's purely group theoretic result, and I was often in the model theory conferences. So that's the locally finite, groups of finite centralizer part, and then I will simultaneously discuss about newer results, observations about pseudofinite groups of finite centralizer dimensions. So yeah, so that's what I will talk about. So let's start. I will have 2 parts in this talk. So part 1 is introduction. So the introduction part will be very short and maybe a little bit boring to some of you. I will just basically tell you what are locally finite groups, what are pseudofinite groups, and say 2 words about this centralizer dimension condition. And then in the second part, where I will really discuss about the structure of these groups, I will do it simultaneously, because we will see when we see examples that though they are both classes, locally finite and pseudofinite groups, they are classes that generalize the class of finite groups. They're actually very different, so we'll see different kind of examples. But you can give them almost similar structural theorem by looking at what is called the soluble radical and then what is called kind of the so-called of semi-simple part. We will see what all that means. So that's why it's kind of a topic that is easy to, everything is easy to talk about at the same time. But so first introduction. So I will first say that in this talk we will consider, so first, like I said a couple of times, locally finite groups. And this is very easy to define, so I'm already writing here every finitely generated subgroup is finite. And then we will consider pseudofinite groups. Well, then more or less at the same time. And so I will define them properly, but let me just write down here first what it means. Something that is elementary equivalent to an outer product of finite groups. And so this part I will properly define, which perhaps is a bit boring for some of you, but then at least everyone knows what are the groups we are talking about. So here, finite, and in this talk, both of these groups under this finite centralizer dimension condition that I will also say a couple of words about. So let's start with defining these groups. What are pseudofinite groups? Okay, so this is not a model theory talk, this is a group theory talk. We only need to know from model theory, from logic, what are definable subgroups, what are definable sets, so that we can talk about definable subgroups. And then about elementary equivalence. So since it takes only 2 minutes, I'm going to do that, so everyone knows. And then I will briefly do the outer product construction too. So just for groups, we fix the language of groups. We have the constant, 2 function symbols, and then any group we can consider as an L group structure by just interpreting them in an obvious way. And then what definable means, definable sets are, as I think almost everyone, perhaps everyone knows, just solution sets of first order formulas, and the first order formulas are just finite strings using variables from here, logical connectives, equality, parentheses, variables. So for example, let me write definable sets. Definable sets are solution sets of L formulas. For example, we have things like phi x for all y, yx equals xy. This is, of course, defining the center of a group. So center of a group is definable. So these are definable sets. And the first order properties, I will talk about first order properties. I will say that first order properties that are true in here are going to be true in here. So first order properties are just given by L sentences. So formulas where there are no free variables So first order properties are given by, oops, okay, I'll take a new one. Sorry. By L sentences. For example, we can have things like sigma is saying for all x, for all y, x, y is yx, and of course then we say that the group satisfies this, sorry, sigma here, if and only if group is abelian. Okay, so this is basically all we need to know. Now we can define elementary equivalence. So two models, two L structures for some fixed L are elementary equivalent if they satisfy the same first order properties, and it is denoted. So elementary equivalence, I will write it here. Equivalence is denoted as usually like that. Right. So now I can properly define pseudofinite groups. Well, I still say 2 words about algebra products, but now, so we fix language L, and we consider family Mi for some index set I, and U an algebra product of I. Yeah. Thank you. Filter on I. So this just means that it's picking the large sets on the power set of I. It's containing I, omitting empty set. It's closed under supersets and intersections, and it's a maximal one. And the non-principal that there is no one I, which is dictating whether you belong to there or not. Okay. Then we denote M star, just the Cartesian product of these MIs, and now we can define M as M star constant by equivalence relation, and I will denote it like this. MI, I will write and say what that is, but let me first write here. This is an algebra product of MIs with respect to U, and here this is just saying that if you take tuples from here, they are equal if and only if they agree almost everywhere in this MI. So we write xi, yi, if and only if this set is large, meaning that it belongs to the autofilter. Right. Now, definition. Well, okay, let me, one more little thing before definition. Note, why do we do this is exactly what I already mentioned. We do it so that now all first order properties that are true in here, well, first order properties are true in here if and only if they are true for in ultrafilter many MIs, meaning that the ones that it is true is forming a large set. So note, first order properties are true in M if and only if true in ultrafilter many MI. Right. Now I will write the definition. Okay. So an infinite structure M is pseudofinite if, so I will write two equivalent things. If M is elementary equivalent to an algebra product of finite structures, MI finite of increasing sizes, because I'm saying infinite here, of increasing sizes. And using this note called Walsh's theorem, this is same as saying equivalently, we could say that this M is a model of the fin, so theory of all finite structures. Okay, so often pseudo-finiteness is defined by just saying if you have a sentence that is true in there, you can also find a finite model so that it's true in there, and then using Wasser's theorem, so this note here, you check that that's actually equivalent for both of the definitions I gave in here. I gave them like this because these are easy to see when we are going to go to examples of pseudo-finite groups, that okay, when you are or are not pseudo-finite. So here is now our definition, and so in this talk we will always think about group, and okay, almost always, and a little bit, couple of times pseudo-finite fields as well. So you can think of pseudo-finite groups as something elementary equivalent to algebra product of finite groups, and similarly to fields, even though fields are algebraically classified. And you should note that you really need to have the elementary equivalence because of the cardinality reasons. You cannot have their isomorphism. Okay, so that was the definition of pseudo-finite groups. Let's now see examples and non-examples of these groups that we are considering. So first, so Z plus is of course not locally finite. Everyone sees that. This is not locally finite and not pseudo-finite, because you can have a sentence saying that if the map sending x to the 2x, x plus x, is injective, then it's surjective. This is satisfied by all finite groups, but it's not true in here. So this is not pseudo-finite, and this part, because sigma is injective, not surjective, not true in. So this is an example of something that is not locally finite and not pseudo-finite. Second example, proof for two group. So this is group defined like this. This is 1 for some n. Now again, this is not pseudo-finite. And exactly for the similarly reason as in here, now you just replace 2 with the p here. So this is not pseudo-finite, but it is locally finite. It is locally finite. By the way, I keep now noting LF and PF, so I don't have to write all the time. So this is locally finite. So all subgroups of this group are actually finite. So it's clearly local. In particular, all finite related subgroups are finite. Then we can look at R plus. So this is elementary equivalent to CP, cyclic group of order P. So here we have that this is a more, so the theory of divisible Thorson-free abelian groups is complete. So we have here elementary equivalence. So this is pseudo-finite, but clearly it's not locally finite. And similarly, we would get here Q plus is pseudo-finite because of this, but clearly not locally finite. Then let's give an example of something that is both, and then something that depends on the field. So 2 more examples. So omega categorical groups meaning all models of size omega are isomorphic. These are just by Rulnar-Chevsky theorem, they are locally finite. And then, now I forgot by who, but it's proven that if you consider a group P, which is called extra special P group, P odd. So this means that the commutator group is wait, no, did I forget? This is equal to the center of the group, which is just CP, and here you have something which is elementary abelian. Elementary abelian. So this is pseudofinite and omega categorical. So we get something that is both. And then final example. All elements have order p. Not powers of p, but order p. So P group means all elements have orders of powers on P, and then when you say elementary abelian, they have all power of P. So elementary doesn't mean in model theory sense.
So exponent is P.
Yeah. Yeah, exactly. Yeah. Right. And then, so I will soon discuss about simple groups in our context. Now I will have one example here. Things like PSL2F. So this is, of course, SL2 constant by the center of SL2. This is just matrices from TL2 whose determinant is 1. This is pseudofinite precisely when the field is pseudofinite. So here there is a bi-interpretation between group and the field. So this is precisely when this F is pseudofinite, which either, if you don't know what are pseudofinite fields, you can take the definition I gave. And if you know, then you know, and actually these are algebraically characterized. So this is when the field is perfect, pseudo-algebraically closed, and quasi-finite. But I won't be using, this is axis result. I won't be using that, so I put it in the brackets. And similarly, this is locally finite precisely when your field is locally finite, and this so locally finite, again, the definition is the same, and finite generated subfield is finite, and this precisely means subfield of the algebraic closure of, well, let's write it out, of a prime field, FP. Okay.
Is it special about PSL?
No, it's not special about, I just took PSL2 because PSL2 is the smallest, well, simple example when the group is simple. So it's not. So I will talk about simple groups in our context, but it's not, you know, you have all groups of Lie type if you know what, yeah, yeah, indeed. So it's, this you can replace by X, denoting the Lie, but that I will say that later on.
Sorry? The definition of pseudofinite here is equivalent to the one you gave in the beginning?
Well,
for groups.
Yes, so in the beginning this is the first definition I wrote down. In the beginning I just wrote, I wrote, which is precisely what is written in here.
Why? But why, the
GIs are finite groups here.
Most of the GIs have to be groups. Is that the problem? No.
Yeah.
If G is a group, most of the GIs have to be groups. To replace them with
you many, and so then you have fun.
Maybe you didn't say increasing sizes.
Increasing what?
Increasing sizes. So the point is that here I have infinite. You know, you have infinite. So if you take an alpha product,
you don't need to. So you okay.
Right. So if here I wrote infinite, so the things in the alpha product have to be of increasing sizes. But often, and in this talk, I think I will also do that. Often pseudofiniteness is considered finite or infinite and pseudofinite. Well, I do in this talk because I said that it extends the groups of class of finite groups. Right. Okay. So that was what are pseudofinite groups and examples of what kind of groups we are considering today in general. And then for the rest of the talk, actually, we will be in this context of finite centralizer dimension. So let me just define that. It's very easy. And I will. How come I'm breaking all the chalks? I will write it like that. Okay, so let G be a group. Let G be a group. Now, if the longest descending chain of centralizers in G, of course.
Set.
Sorry?
Centralizers of set, I assume.
Yeah, centralizers X x1, x2, where x, so sets in x and 1 and so xi belongs to G.
But the descending or ascending is not. You seem to be writing an ascending chain.
Ah, yeah. But no,
descending. I see.
Yeah, indeed, yeah, descending. But it doesn't matter. You can take descending or ascending and then just take the double centralizers. And if you have a descending, then you are going to get for ascending too by taking just the double centralizers and putting everything other way around. But I'm writing descending because I usually write this. So same as saying, yeah, I'm writing descending. Has length k. Then this G is said to be of centralizer dimension, and again I will write just CD because I don't want to keep writing long words. K, and if such K exists, then G is of finite centralizer dimension.
So that's a surrogate of Morley rank, right?
Sorry?
That's a surrogate of Morley rank.
No?
No?
But that's what? I just heard Tas and Morley rank.
What's a surrogate of Morley rank?
You mean that for groups of finite Morley rank they have a descending same? Yeah. So for stable groups, but for stable groups they have DCC actually, so it's even more than.
So it's like you want to work outside of stable groups.
I don't. So I'm not talking about. I won't say there will be no stability. There will be no groups of finite Morley. This is not. So when I've been talking about these things, yeah, when I'm actually going to talk about results that I've been using to classify certain groups of finite Morley rank. But that has been the time when I'm stating this result, not saying a word about that, and then being in the model term. Now I'm talking. There will be no. There wouldn't have been a word Morley rank unless you brought it up. So it's okay, but I won't say it again today. Well, in this talk. Or maybe, okay, I don't know. If such K exists, then G is of finite centralizer dimension.
So descending is strictly descending.
Yeah. Strictly, of course.
Strictly, yeah, because it's still, strictly, yeah. Long as strictly. Okay, so things like, well, obviously we have abelian groups. We have things, if we think about here, so we have GLN, K, KA, well, let's put that here, KA field. That's what we are going to have. We have, let's do stable groups. We have stable groups. We have groups that are elementary equivalent to algebra of groups, finite or infinite, such that for ultrafilter many i's, this GI is of centralizer dimension K. So if you take ultra product of things where you fix the centralizer dimension, then you get again something here. Okay, so this is the, these are now, everything is defined. What kind of groups are we looking at? We are looking at locally finite and pseudo-finite groups which have the finite centralizer dimension.
So also closed subgroups of point D, right? So,
yeah, indeed. So subgroups, of course, are, sorry. GLN and subgroup. So if you have a DCC on centralizers, every subgroup also has DC on centralizers. And similarly for the locally finite and pseudo-finite groups, subgroup of a locally finite group is again locally finite, and definable subgroup of a pseudo-finite group is again pseudo-finite. And for the quotients as well, so a quotient of a locally finite group is again a locally finite, and definable quotient, so quotient by a definable subgroup is again a pseudo-finite.
But in item B, K is an arbitrary field. Yeah?
Sorry?
In item B, K is an arbitrary field?
In
B, example B.
So in here, it is an arbitrary field, and this, and K, so because you said K, but I was thinking about the centralizer dimension K, so the centralizer dimension K depends on the N. Yeah, but here it's another. I could have brought the fields or product of fields or stuff like that. I just brought field now because we are going to have soon things like subgroup C and K over pseudofinite or local finite fields.
What's the dimension of J and K?
Sorry?
So what's the dimension in case B? Is it n?
You mean centralizer dimension?
Yes.
I think it's n square minus 1 or something like that. So in PSL2 it's 2x. It's bounded, so it's bounded easily by n, but now it's not n. It's not exactly n in general.
Bounded by Norwegian, perhaps.
Right. Yeah. Okay. Perhaps. So good. So now we move on to the second part of the talk. Structures of both locally finite and pseudo-finite groups of finite centralizer dimension. Okay, so what we want to do, I will first explain to you what we want to do and then I will go to details. So what we want to do is that we start with the group G, either locally finite or pseudo-finite, always of finite centralizer dimension, and we want to show that we can build a normal series of actually definable subgroups, but I won't pay too much attention on that, so that we have one here, and here we have what is called the solvable radical of this G, which is a maximal normal solvable subgroup, and we will see by results of Kukro and Wilson, so by Kukro in the locally finite case, and in the Wilson by Wilson and Kukro in the pseudo-finite case, that this is well defined, this exists, we can plug it in there. I will show it to you. And then we want to see that kind of what to put here. And what we want to put here is that we are looking at, now that we have, or once we have this radical, I will call it just a radical, so I will define it later. We are looking at this group, and we are looking at first what is called the SOCL of it. So I will properly define and I will tell you how to properly see what it is, but this SOCL in general for a group is just defined as group generated by minimal normal subgroups, and we want to plug here the premits of this guy. This is what we want to do. Now in the locally finite case, we can do it properly, nicely, everything is good. In the pseudo-finite case, actually what we are going to do is that we are going to look at the ultra product of the SOCL, so there will be GIs in here, and then we are going to find here premits, and so in the locally finite case it was just like this. Since I'm only roughly explaining now I will leave it like that. And so we want to do it in such way that we can describe fully this quotient, and what we are going to see is that this is in the locally finite case finite, and in the pseudo-finite case abelian bifinite. So the results are going to be a little bit different, but actually everything is quite similar. So now what I have to do is, now I realized I got confused with all these questions in the finite centralizer groups. What I should have said, and which I will say now, it's good I left it here. What is the problem, or what is the thing to consider when you are considering groups of finite centralizer dimension? It's inherited by the subgroups, but it's not inherited by quotients. So this is the kind of problem in general when group theorists are looking at groups with finite centralizer dimension, is that if G is of finite centralizer dimension, it doesn't mean that its sections are. So then we have normal subgroup of a subgroup. We don't know that this section, this is called the section, we don't know that this is a finite centralizer dimension. So this may not be of finite centralizer dimension. So the whole point will be, well, first we have to be able to have this radical, which we will get from the results of others, and then kind of, first of all, is this quotient here, how to see that it's a finite centralizer dimension, or if it's not, well, it will be, but even before we see, to see some weaker conditions that are passing here from the group, so that we can do this, all this. So that's what we are going to see next. And so to do that, I have to talk a little bit about, so that I can define this SOCL, I have to talk a little bit about the simple groups in our context.
Can you say something about the quotient divided by the radical?
Yeah, can I say something about, yes. So I can say that, so this is same, this is in the rad. This will be in the, exactly. This will be in the locally finite case exactly the case. Yeah, exactly the case. And in the pseudo-finite case, you have to be a bit more careful because we are just getting stuff that is elementary. But I will state it properly. But yeah, indeed, perhaps I should have said that already there. Right, so towards that, first tool that we have to look at is simple groups. And now everything is always in our context. So first, I will recall the classification of finite simple groups. So a non-abelian finite simple group. So simple group means no non-trivial proper normal subgroups. Simple group is either alternating group for n bigger or equal to 5, group of Lie type, or one of the 26 exceptions that I won't say anything about. Now I want to say 2 words about this. I don't want to say too much. So if you know what is a group of Lie type, that's great. If you don't know, it doesn't matter in this talk. So I will just say that they come as finitely many infinite families. So you have 16 families, which are called AN, BN, CN, DN, E6, E7, E8, F4, G2, plus what are called twists, but I won't say anything about that, so don't worry about that. And so just to give you an idea, AN is PSL n plus 1, A1 is PSL 2, so plus 1. So if you don't know what these are, then just think of something you know. Just think of PSL2 or something else that we know over a finite field. And now, from now on in this talk, from now on in my talk, when I write XF, I mean one of these groups. So I fix the type. So here, for example, the PSL. And I also fix, so this is called the Lie type. And I also fix the rank, called Lie rank. So this X is fully fixing. This is my Chevalier group of this type, of this rank, over a field F. And our F will be either finite, when everything is nicely done, or pseudo-finite. And then because these groups of Lie type, they are uniformly definable. So already it was told what it means. It means that there's a first order formula which among finite fields is giving you the fixed Chevalier group. And it is given by a product of bounded limiting conjugates. So over pseudo-finite fields, we just get, Chevalier groups or pseudo-finite fields. They are definable over the corresponding fields. And even with the twists, everything goes well. So the groups of Lie type are well defined for finite, for pseudo-finite, and as well for locally finite. So for locally finite, again, not all of them appear over all locally finite fields. So for example, if you take the FP alg, then the field is algebraic closed, so there are no more twists and stuff. But none of that matters in this talk. So just when I say from now on XF, and I will always specify which kind of the field we have, it just means that it's something that we already know. It's classified. It's already know. That's what I wanted to say. And now, so how do simple groups look in our context? We have here the classification of finite simple groups, and we are going to have nice classifications also for pseudo-finite, infinite pseudo-finite, and infinite locally finite groups that we can then use to define these so-calls. Oh.
When you say pseudo-finite, do you mean it's definably simple, or do you mean it's simple? Simple. If I mean definable simple, then I will say definable simple. Which I was supposed to say at the end, but I don't think. No definable proper normal subgroups. So here, so it's just always when you say definable, then it's just okay. So theorem by Wilson
And now I forgot the year up to isomorphism by Rutten, I think 2007 up to isomorphism. Someone who knows can remind me of the year. An infinite simple pseudofinite group is isomorphic to a Chevalier group over a pseudofinite field. Okay. So in the pseudofinite case, we have a nice classification theorem. This is by Hartley, 95. And now that I say 95, I have a feeling that this is 95 as well. Theorem by Hartley. An infinite simple locally finite group which such that not every finite subgroup is a group is a subgroup of, so let's put G somewhere. An infinite simple locally finite group G such that not every finite group is a subgroup of G is isomorphic to XF F locally finite. Now we will see that this is going to give us classification of simple groups in our context, which is locally finite plus finite centralizer dimension, and it is done by Thomas. So Thomas proved, I'm not writing it here just because I'm starting to be out of time, but Thomas proved that if you just take an infinite simple locally finite group and add the finite centralizer dimension, then you precisely get this. You get the Chevalier group or group of Lie type over a locally finite field. But for us, it's not enough because we have to look at the socle of a quotient, and we don't know that it's a finite centralizer dimension. So we are going to use this Hartley's result to classify simple groups in our context. That's why this is the one that I'm stating.
When you write isomorphic, do you mean it's definably isomorphic to a field which happens to be definable?
Yeah, so the field is here bi-interpretable, but this is so.
No, but what I meant, the isomorphism, is it an abstract isomorphism or is it a definable isomorphism?
No, here it's an abstract isomorphism, and here this is I think it's an abstract isomorphism in both of them. But here, am I saying nonsense in the pseudofinite case? Here there is a uniform by interpretation, but here no. This is, but you know, this is. No, yeah. So here you have a uniform by interpretation.
With X, my question is the isomorphism. So you start with a group G.
Yeah, but I don't remember exactly how Rutten did it. That's the problem. Okay. But maybe I think maybe the.
I thought what Ren did was to show that these groups are uniformly bisurface with certain difference fields.
Yeah, so the big.
From the group you can construct the field in a definable.
Yeah, because he needed to, especially in the twisted cases, he really needed to take the ones where you have the properties of the morphisms to write. Yeah, you are right, exactly. Yeah.
There exists a field which is defined
yeah,
in the group.
Indeed. Yeah, indeed, exactly. Yeah. Yeah. Good. So this is. Sorry, was there more questions?
So is that this final CD assumption or not?
So here, no. Here, nowhere, no. So I just pointed out that for the locally finite groups with this assumption, we also get this by, okay, let me just write it down here just because I feel bad of not. So Thomas proved, here, no finite centralizer assumption ever. Here, it doesn't exist. And Thomas proved that an infinite simple locally finite group with finite centralizer dimension is isomorphic to. So if you add it, then you get it. Is isomorphic to, again, Chevalier group. But as I pointed out, this may not be enough because when you go to quotients, you may lose the finite centralizer dimension. Okay, so this is simple groups in our context.
And is that has the same dimension, or the dimension is bounded in terms of the dimension? No.
Sorry?
So you're saying if it has finite centralizer dimension, right?
Yeah.
So what is, can you say what is dimension of F?
Dimension of. No, because it's because the centralizer. If you take a Chevalier group, it's bounded by the Chevalier rank. The finite centralizer.
No, I mean for the F.
No,
no, because it's not, the centralizer dimension doesn't depend on F, it depends on the, here you end up having a Chevalier group, which has the Lie rank, and the centralizer dimension depends on the Lie rank, so it has nothing to do with the, yeah, indeed, yeah. But I mean, yeah. Sorry?
The second thing looks, not the second, looks weird because the direct limit of ANs satisfied the assumption, right?
But no, because it has a normal subgroup. This, if you take the algebra product of ANs, you end up having a normal subgroup, but not a definable normal subgroup, and that's where comes your question that definably simple and simple groups are different. Because if you take AN, something that you know fixed almost nothing and fixed almost everything, you are going to end up having a normal subgroup in the algebra product. So it doesn't. So this.
I'm just taking the union of ANs.
Where? So sorry, you're talking about here?
Yes.
Oh sorry. Yeah, but then you are not gonna have all. So here I don't know, but I mean I don't know exactly how he killed that situation, but I think it was quite a big theorem.
Yeah, sure.
So I don't know exactly how you kill this situation, but so this condition is gonna kill it. Here there is no finite centralizer dimension indeed, so I cannot kill it with the sorry, I was talking about this when you asked. But here it must be that you can just find I guess maybe you can find a. I guess you cannot embed all up to very high solvability degree, which is exactly what we are going to do next in our case as well. So now circles and radicals, and again in our context. So G is a group. The solvable radical. Rad G is the largest solvable normal subgroup if exists. Okay, and so Wilson proved, now I have a feeling that this was 95. Now it might be that my years are off, sorry. So Wilson proved that among finite groups, the solvable radical is uniformly definable. So there is L group formula phi x such that when you take a G finite. Now I started to hurry, sorry. So you take a finite group, then there is a L group formula such that the solution set is the solvable radical of G. So this gives us, in the pseudofinite context, it gives us a subgroup. It gives us a definable normal subgroup, which may or may not be solvable. It depends on whether you can bound the solvability degrees of the finite groups. But by result of Cook-Rowe, we can, in our context, Cook-Rowe, 2009, he proved that let G be a group of centralizer dimension K if one of the following holds. Then G is solvable of derived length bounded by K. And what are these two cases? First, if G is locally finite and solvable. So in a locally finite group of finite centralizer dimension, the derived length of solvable subgroups is bounded by the centralizer dimension. And two, if G is elementary equivalent to an outer product of solvable groups, outer product of finite solvable groups. G are finite and solvable. So now, when you have now this is telling us that the soluble radical is well defined both for locally finite and pseudofinite groups of finite centralizer dimension, because when you take a pseudofinite group, then you take the solution set of this formula. It's a definable subgroup who is elementary equivalent to these radicals of the finite groups, which are soluble, and now they are soluble by bounded solubility degree. So this means that in our context, I'm just going to write this is well defined, is this radical is soluble of k-bounded derived length, and by that I mean in our context, when you have a locally finite or pseudofinite group. And that in particular allows us to now generalize the result of Thomas, because this, okay, it's behind here. This phenomenon that we want to explain both for locally finite and pseudofinite groups of finite centralizer dimension, where you find this normal series. So the locally finite case was done with my supervisor 2019, and simultaneously with Puturlakin with a little bit different proof. And the first thing we did is that we observed that actually, while the centralizer dimension doesn't go to the quotients, this thing that you have bounded soluble degrees goes to the quotients. So the first thing we observed is that, I will just write it as a lemma. It's not very hard. Borovik, myself, and simultaneously by Puturlakin, also 2019. The first thing we observed is that if G is locally finite group of centralizer dimension k, then the derived lengths of solvable subgroups of any quotient of G, of any section. So remember, I defined section of G. I defined it earlier, so it was the form quotient Kn, where K is the subgroup and N is a normal subgroup of K, is K-bounded. So though the centralizer dimension doesn't have to go to the sections, the fact that we can bound all the derived lengths of all soluble subgroups does go down. And this in particular is saying that if you take, you can write it as a theorem, Hartley plus lemma is saying that, plus lemma above is saying that let G be a simple section of a locally finite group, of finite centralizer dimensions. Then G is isomorphic again to XF, where F is locally finite. So we actually generalize the result of Thomas by going to all the sections by using this result of Kukro about solubility. And now we have exactly the kind of result where we can define properly the circles in our context. But let me just see how much time I have, if I should hurry. Oh, I should hurry. Okay, so I will not write down very precisely, but now the point is that what one can now do is a locally finite case is that you can well define this quotient, and you can take its circle, and you know how the simple groups are, so you're going to see that the circle is actually just a direct product of finitely many simple non-abelian groups, each of which is either finite or isomorphic to Chevalier group or a locally finite field. And the fact that there is this M that you actually can find only finitely many follows because, well, I don't have time to go, but there is a procedure that you can start building these normal series and then use some results about locally finite groups of finite centralizer dimension, giving you this M, which only depends on K. And moreover, we proved, I'm writing it here quickly, we proved again, now I'm just writing Borovik, Karhumäki, Puturlakin, if G is locally finite of finite centralizer dimension K, then actually this is also of centralizer dimension K prime, where this K prime depends on K only. So my plan was not to talk about this, but kind of where it's not needed. So eventually we proved that actually the centralizer dimension goes down for this particular quotient, but it was not needed for example, seeing how this circle looks like. But now I got a little bit messy, so let me state at least both of the theorems properly and say a couple of words about the other quotient. Since I started a bit late, maybe I have until 5 past, or no?
What do you mean the end of the sentence?
Sorry.
No, but it's not like that's what to read.
If G is a locally, then it's also of centralizer dimension K prime, where K prime depends on K only. The word depends was not done. Yeah. Okay, so I will just now state both of the theorems. So first for the locally finite group, let's write theorem A, and so as I said, this is by myself and my supervisor and Buturlaking 2019. Let G be locally finite group of centralizer dimension K. Then there is normal series 1, the radical of G, L, where, as I said, this is, so this the Cook-Rowe proof that this is solvable of Kane-bounded derived length. I'm not going to write that again, but where this this L, which is just sorry, it's L quotient is radical isomorphic to a circle of like that. Is L1, Lm, where Lj is simple non-abelian finite. So it's a long finite or isomorphic to a group of Lie type, where this F is locally finite, and this quotient is finite. Okay, so this is the locally finite case. You get that this is solvable of derived length bounded by the centralizer dimension. You can precisely describe this group, and L is just the pre-image of that, and this quotient is finite. And in the pseudofinite case, I'm just going to modify with a different color. So in the pseudofinite case, if we put here pseudofinite, then you have definable subgroups where this L, let's denote it by K, and then instead of A and B, we have that, let's write like this, A. If we take alpha product of these, indeed, so it was a bad idea. So, is it better? GI, so now our group is elementary equivalent to GIs. This is of the same form again, but this time these LJs are over pseudofinite field. It's a direct, sorry, yeah, this because I corrected myself. It's a direct product where as in A but F pseudofinite. So exactly the same conclusion. This M only depends on K, and you get the simple non-abelian groups which are either finite or locally finite, here pseudofinite. B, there is some K bar, which is a definable subgroup of G grad G, such that this K bar is elementary equivalent to this S. Okay, now this is getting very messy, I'm sorry. And this G, K is abelian by finite. And I'm just going to say that you cannot get finite there because there are examples where it's infinite. And okay, so I will finish by saying, I'm sorry, this got a bit messy. So the pseudofinite part, let me still put here, theorem B, this is the pseudofinite part. It's my result from 2021, plus in the end that this is abelian bifinite and it cannot be proven that it's finite. It is communicated. It's something we proved in a special case with Pinar, but we didn't actually put the whole general thing there because we needed it only in a very special case, but with Urlu. And so this, why I wanted to do this kind of result once we know this one is because I actually wanted to prove and show using this that there are no finite generated pseudofinite groups. There are no infinite finite generated pseudofinite groups of finite centralizer dimension. But okay, perhaps I went a little bit over time. Sorry.